Hello, uh, welcome to my video on my PID project. Um, this is a ball and beam balance system. So essentially what happens is a ball rolls around. PID control is used to measure an input from the user that sets a certain position along this beam, at which a distance sensor, either ultrasonic or laser, would be used to measure a reading. From that reading, an error is determined, which is the system response, which is the difference between the system response and the user input. And with that error, PID control is used to balance the ball at that certain location that you want it to be at. So for example, right in the middle would be a set location, and over here at this end, the distance sensor would measure a distance delta x, at which that delta x is passed through an algorithm in our microcontroller, and this servo would react from that, kind of actuating back and forth until it sits at the final spot. Ultimately, with PID control, some of the major characteristics are to maintain good tracking and to reach a steady state condition. So kind of going over the build of this whole project. Most of the material that you see is bought online from Servo City, specifically the hardware, so or the body, which is made of all aluminum. So this is an aluminum C channel. It's 12 inches long. This is the A bracket. This is a stainless steel shaft. These are aluminum pillow blocks, aluminum shaft collars, aluminum base, 1-inch C-channel, servo mount. All this is from Servo City, and then most of the electronics are outsourced from other websites. So going into that a little bit, I'm talk about the servo motor is a Tower Pro MG996R. It's a pretty good servo. Only issues I have with it is it's also a 180-degree servo. It has a fast response time, but dealing with servos can be difficult. Right here, I mean, it's on a horizontal. That's about as horizontal as I can get it. So there's when you do it with the servo, there's the issues with the degrees in between, and so it's a little bit hard to code with that. And then also it takes 5 volts, which was shorting out my board. If the gains were getting too high, the board would short out my Arduino board. So that takes me over here to our electrical and board setup. Right here I have a YW robot. It's a breadboard power supply, so it feeds 5 volts to the breadboard from this wire. It's just a plug-in 5-volt power supply, and then the cables get jumped to the servo. And the only pin that's connected to the Arduino from the servo is pin 9, which is the output or input to the servo. I believe PWM input. And this is Arduino Uno from Service, or I'm not sure where it's from. And then our 2 sensors that we're using in this project. One is the VL53LOX. So I chose this one because it has a good, pretty accurate for a laser sensor. Also relatively cheap, only $15. Unfortunately, I think I burnt it out when, or before I had this connected. The servo was, every time, like I said, high gains occurred, it would reset the whole Arduino, and then I plugged in a separate power supply, and I think it was too much for the for this guy, even though this has a voltage regulator. I don't think it handled it. So my fallback sensor is this HYSRF 05 ultrasonic. It's one of the better ultrasonic sensors that you can get, I believe. So yeah, that's what we're using. And then just a little bit of hardware from hobby shops, nuts, bolts, etc. So let's go ahead and I'll get my computer going, and I'll go ahead and show you the code. Alright, so now I got my PID codes up. The one on the left over here is going to be the code written for the ultrasonic sensor, and the one on the right is the code written for the laser sensor. The laser sensor is obviously not used, but I did have a code written for it. I was testing it before it failed. So they both begin in a similar manner. I'll just focus on the sensor code over here first. So to start, I just included the servo library and the PID library. To understand how the servo worked and understand how the ping worked, as well as the for these two, Arduino has the built-in libraries for each of them. So I used both at first to kind of figure out how each one works, find the optimal ranges of the servo, as well as the maximum distances of the sensor, at least what I would need in my case. So I just included those, kind of following what the examples have, and then included the PID library, and these can be found if you just go to Sketch, include library, manage libraries, and search for each one of them, or you just go to File and open up the example for the servo motor or for the ultrasonic sensor. So kind of getting down to the most important part, here are the PID gains. So KP, KI, KD. And using Zeiger-Nichols method, I was able to find these values, at least a range for these values. For the KP, good range was from about 1.5 to 3.0. And really it was just about finding the optimal setting for the ball and beam system that I have. So those are the values, and those are the ones I'm going to use in this video. Going down a little bit more, this is just the setup for the sensor, very straightforward. Over here I have output limits for the servo motor. So then scrolling down, this comes mostly from the PID library. And the set point I'm using in this video, which you'll see in a moment, is going to be 11 and 25. So that's going to be centimeters. And if you look at the beam that it rolls on, at this end, this measures from 0 to max centimeter range from the echolocation. And for the beam, it's actually 12 inches long. So at this end, it'll be 31 centimeters, and at about the face, it's like something like 3 in this range. And right now, I believe it's reading, if I bring up the serial print, it's reading 5. So right now, it's at 5 centimeters there. So what it does is it reads the value. My PID computes the error. So in this case, the error is going to be 23 minus 5, which is 18, and then it processes all the gains using the error, and the servo output, it outputs it in the servo output. So output is what occurs inside the compute function, and then 65 degrees is my horizontal servo position, which is right here. So this is 65. If you rotate down, that'll be towards 180, and then going up is towards 0. The ball's just going to roll over the serial monitor. I will have it up, and I will be showing the output and where it is and whether or not it steadies out. And as I said before, I'm going to run it at 11 and 25, and that'll happen right now. So enjoy the next few minutes. Okay, so after watching those clips, I think you can see that the ball and beam system works very well. The ball is balanced at the front end very quickly. The system response is very fast, and there's a very quick convergence that occurs in the front end. I believe it's a robust system off the way it's built and off the way that the code is set up. The gains, they don't over-actuate. It's not too much oscillation. So I think the gains are at an optimal level. You may have noticed that on this end there's quite a bit of oscillations, and it doesn't really steady out. It doesn't reach its set point and balance out. It kind of wobbles here and there. I believe that is an issue with inaccuracies occurring with the ultrasonic sensor, as well as the setup down here. I think if the ball was sitting lower within the channel, as well as the sensor, I think that there would be a much better result. I also believe that with the laser sensor it would work flawlessly the way it is. So those are just some final thoughts. Thank you for watching my video. It was an enjoyable project to make, and I am pleased with the results. I wish the sensor worked up here, but overall I'm pretty satisfied that down here it responds the way it does and it bounces the ball. I hope you enjoyed the video, and thank you for watching. Bye.